Good afternoon, everyone. I am Aman Rawat, chairperson of IEEE TCT, and it gives me immense pleasure to welcome you all to this webinar on quantum computing. So, just a basic gist about quantum computers. They harness the unique behavior of quantum physics, such as this superposition, entanglement, quantum interference, as we've all learned in our 11th and 12th, and they apply these concepts to computing, and this introduces a whole new domain, and this introduces a whole new concept to traditional programming methods. And it is astonishing how technology has grown over the years. The phones that we use today are a million times powerful than the computers that landed the Apollo 11 on the moon. Now, to help us understand more and gain better insight on this topic, we have with us today our speakers. Firstly, we have Mr. Aritra Sarkar, a final year PhD candidate at QU Tech in Netherlands. Sir has had a wide spectrum of experience, having worked in Conscientia, TCS, and ISRO Satellite Center. Secondly, we have with us Mr. Aritra Sarkar, a doctoral researcher in quantum technology at Chalmers University in Sweden. And he has also had a lot of experience having been a part of institutes like Tata Technologies, IMEC, and more. And last but not the least, we also will have with us Rishi Sridhar, a quantum information theorist and a master thesis student at Chalmers University. Now, sir, without taking much of your time, I would like to hand you over this session. Thank you so much. Aritra sir, so you're also on mute, I think.
So is this good enough? Already see everything?
Yes, it's good.
Yeah, so I'm Aritra, and Aman already did a really good job introducing me, so I won't reintroduce myself again. So today, in this two sessions that I and Achintya have planned, initially I'll be talking a little bit on quantum computing. Why do we need it, and what exactly is quantum computing? And then Achintya will take you through more details on how to get involved and what are the different like this educational fields that you need to study to get involved in a much broader variety of quantum technologies, where quantum computing is only one of them. So quantum computing has been like all over the news recently, and unless you are living under a rock, you would have heard this name quantum computing. And like we see a lot of news articles from like popping up everywhere around us with different very like hyped news. So there must be some truth to it, of course. It might be like a problem that only a quantum computer can solve, which immediately means that it can do something that no other computers can do. There are results on experimental quantum computing, which says that we can already build a quantum computer that can beat any other classical computers. Like that's the type of computers which include your mobile phones, your laptops, or even the supercomputers at like the different data centers. Again, quantum computing is also might be having some features that even Einstein weren't able to fully understand the reasons behind. There is something called as the quantum internet, and it's still being built. So these are again the things that is happening in the quantum world. And often these news articles, at least the heading of this news articles, try to draw your attention towards this. Like they are sometimes very super fancy, that how will quantum computer help unlock immortality, for example. Of course, it's not going to make you immortal, but there is again some truth to these news articles, that maybe it discovers a drug that's going to help you fight some cancerous diseases or so. So in this talk, mostly I'll be telling you why, like what exactly started this research in quantum computing, and then into like the what exactly is quantum computing. So in the why part, we are going to look at 3 different angles: physics, computer science, and computer engineering. And in the what, I'm going to take you through what exactly is quantum information, how do we process them, how do we build algorithms from those processing, and finally, what are like the top applications that people are looking at. Okay. So coming to the theoretical motivation, like the 3 fields that made people realize the importance of quantum computing. 2 of them are physics and computer science. So physics, around 100 years back in the last century, we were trying to understand very specific properties, mostly in quantum mechanics. What are the different specific properties, like Aman mentioned, superposition, entanglement, interference, and measurement. And people already understood what these things are, at least the mathematical models of it. And then the next step is, how can we use these more to control systems? Can we build controllable systems based on these properties? And once we learned how to do that, this controllable technologies can already be applied across disciplines to make technologies out of it. And there are a couple of things, and Achintya will be discussing more on that. So that's from the physics side. People were eager to use this mechanism, quantum mechanical phenomena, to build devices. Computer science guys were already very excited just because quantum computing gives a new way of doing computation in general. And they were trying to figure out what these new ways of doing computing can be useful, what kind of new things that we can do with it. And one of them is to reduce the resources required to do computation. By resources, I mean, let's say how much memory you need to do a computation, how much time it takes to do a computation. So by these new forms of quantum computing, we can gain some advantage in this computational resources. So these 2 were the main motivation from the computer science side. So other than these 2, there was like one more important thing, and that's about building computers, building smarter computers. So we know like modern computers are built from transistors. So this is basically what is there in every single computer that we use today. And there's something called as the Moore's law. So Gordon Moore, like the co-founder of Intel, he found out a trend that's happening in the industry. So every 1.5 years, the number of transistors that you can pack, that you can manufacture in a given area kind of doubles. So after 1.5 years, you can pack already like, let's say 2 of them. In another 1.5 years, so it doubles from 2, so it becomes 4. And by, let's say around 4.5 years, from 1, you have now 8 transistors in that same area. So how that worked is basically, when you have smaller transistors, you can pack more of them. So when you have more transistors, you basically have better computers. So they are faster. Now you can have more applications on those computers. And those applications in turn helps you to research technologies that's going to help you make even better computers. So it's like computers designing computers. But over the last decade, people are seeing a slowdown of this. And the main reason is, over here, you see like when you're packing just, 1 second. So if you're packing 1 transistors, the amount of heat getting dissipated is on this area. But when you're packing 8 of them, there are also heat getting dissipated in between, and only it can exit out of the chip from the area of it, not from the volume of it. The heat cannot come out from the inside to the outside directly. So it's getting heated up a lot, and people tried out different ways of reducing that heat. But eventually, when you're making these devices smaller and smaller, a limit will come that you cannot make it any smaller anymore. Like these transistors are basically a switch, an on-off switch. And this on-off switches are getting almost at the size of 1 atom width. And you cannot get any smaller than that, of course. And what's at stake? Okay, this is good. Like you will reach a limit and we won't have bigger computers yet anymore. What's the big problem with that? The problem is most of current economy is dependent on our computers getting old and we buying new laptops every 2 or 3 years. buying new phones every 2 or 3 years, because these better computers and better phones can do something that their previous generation phones and laptops couldn't. So these are the new applications that human civilization is increasingly going dependent on. What can be done? Of course, we don't want that human civilization progress to end. And two of the techniques are accelerators and quantum computing. So that's in the next slide. So one thing that you might have noticed that when you want to play a new game in the market, you want to buy a better GPU, a better graphics card, basically, on your computer. The reason is normal computers, the Intel chip, for example, the i5 or i7 that you have on your laptops, are not really good for graphics processing. So these graphics cards are specifically built to do better graphics processing. So similarly, you can also have a quantum computer, which can do specifically the things that quantum computers are best at. Graphics cards are best for graphics processing. Similarly, there are specific things that quantum computers are good at. And there will still be the CPU. It will still be, let's say, working on your laptop, sending mails via your normal classical computer. But when it takes a specific type of operations that quantum is good at, you're going to send it to this quantum computer. It's going to do this calculation and give you back the result. So probably you won't be playing games on a quantum computer, but who knows? Like when we started off the normal computer revolutions, computers were mostly used to calculate trajectories of missiles in the World War II. And now it's in everybody's pocket. So we really cannot predict how quantum computers will be 50 years from now. So this quantum computer is not one single idea. You need to build up from the ground. So you have algorithm on the top and your quantum processors, the quantum version of your Intel chip, for example, at the bottom. And between this, there are many different layers. There is the programming language, there's a compiler, there is something called as a microarchitecture. And each of these are required to take this high-level description of what you want to do down to the chip and run that thing on the chip. And each of these layers also requires different expertise. Like, for example, in quantum computing algorithms, you need more knowledge of computer science. For building the quantum chip, you need more experience in microelectronics or experimental physics. I'll skip that part. So now you know that there is another motivation, and this is the main reasons why all these big corporations in for example, IBM and Google, these are investing so much in quantum computer, because we need better computers. And if we can make them using the quantum way, why not? We can use those quantum computers to have new applications that we couldn't envision before. Coming to the quantum phenomena, again, like Aman mentioned, there are 4 important phenomena, and in this slide, you'll see 3 of them. The first one is superposition. I'll be describing these things in the next slide in more detail. The second one is entanglement. So entanglement is when you have 2 particles and you set up a very strong correlation between them, such that even if you separate them apart, you cannot describe them by just describing half of it, or describing both of them individually. And the third one is observation. So quantum phenomena happens in a very secretive way in nature. As long as you're not looking classically, you are going to see this phenomena. But the moment you try to observe as a human being, for example, those phenomena will disappear. And there's another secret ingredient. As I said, there are 4 important things, and that is called interference. And in this slide, I'll show you how that works with a very small example of how a quantum algorithm looks like. So let's imagine you have a tiffin box or dabba, and in this tiffin box, you have 4 different foods. There's a possibility that it can have one of these foods inside the tiffin box. And this is kind of like a superposition. The idea is very similar to a superposition. You do not know what's inside the tiffin box, so it might as well be one of these 4. The best way to describe that is maybe one of these 4 is there with 1/4 probability. So this is the food that is there. And each of the food obviously have some properties. So this is the taste, for example. Each of this food has a different taste. And there's a quantum way to entangle them, to pair them up with the properties. So that is basically the idea of entanglement. We have this object and this property, we match them together. So now once you entangle them, there is some things that you want in this and some things that you don't. So the dark blue ones, you don't want to have, let's say, sour or bitter foods, but you are more interested in the savory or the sweet food. So that's where interference comes into being. So you kind of write a quantum function that mixes up only the things that you do not want and leaves off the things that you want. So what would happen is the sour food will get less sour when you mix bitter with it. The bitter food will get less bitter if you mix sour with it. And this is how it works. So you put all of them through. So this is happening in parallel, as you see. And only the sour and the bitter are getting mixed. The other ones are not. So what happens after that is the sourness and the bitterness of those two foods gets reduced, which means that since we are dealing with probabilities, the savory and the sweet foods, the probability of having a savory food or the sweet food inside the Tiffin box increases. That's good. So that's now you have increased the probability of getting a sweet food or a savory food inside. So then you do the last step, which is the measurement. So you open up your dabba and that's another, like, as I said, like you don't see the quantum properties. Once you look at it, it becomes very classical. So you cannot have both these two together in the box. So once you measure it, you only get one of them with some probability. Let's say around 43% probability, you would get the vada pav. With 43 more, you would get the modak. And with the rest 7 and 7 probability, you would still get the sour and the bitter because it doesn't work perfect, of course. If you repeat this experiment the next time, you might get this. So you have to repeat this experiment to understand what are the foods that you like and whether it's there in the Tiffin box or not. So this is the exact setting of a quantum algorithm. In quantum, of course, this is done in a very different way. Instead of the food, obviously we use particles like electrons or photons, and they have this property that it kind of shifts between 0 and 1. It's very similar to the food being in two states at the same time. And so now we have a mathematical model for doing this computation. I'll just quickly go over it, not spend much time on that. And that is represented by each of these two states. The 0 and 1 has some probability associated with it. But instead of a probability, we use in quantum computing a complex number, and that's called as the amplitude. So that Z0 and Z1 are complex numbers like A plus iota B. When we measure them, as I said, only one of the states come out. So that is given by the modulus of that probability. So if you see, for example, the blue ball, it means that you will always see the blue ball with the probability of the modulus of Z1. So if it's like x1 plus x1 square plus y1 square. Again, the probabilities add up to 1. So both this probability together, so Z1 modulo plus Z0 modulo together adds up to 1. So of course, you have to get some outcome from the experiments. Also, you might notice that every time you have one extra qubit, it doubles up the state. So as long as you have one qubit, you have two states. But let's say you have 4 qubits, which means that it has one of these 16 possibilities. So with n states, you basically, n qubits, you have 2 to the power n states. And you can interfere all the states in parallel. As I showed in the last slide, there were like 4 states, the 4 foods. So similarly over here, for example, if you have 4 qubits, you would have 16 such foods that you can interfere in parallel and get your results. Now, you might be thinking, why such a weird model? Why use complex numbers instead of probabilities? Because this is the model that works. This is the model that exists in the environment. And people like mathematicians and quantum mechanics scientists were just trying to model it, and this model fits. How do we program them? There are many different types of quantum computers, which I'll not go into because it's like a lot to learn in the first touch with this quantum world. One of them is gate-based quantum computing, and that is very similar to Boolean logic. So if you're from the computer science or computer engineering background, you might be knowing this Boolean gates that are used for classical logic. Similarly, there are just many quantum gates as well. And you can just pick and place these in your algorithm, and you get some kind of a quantum circuit that you can run in the same way. You can use the superposition, interference, entanglement, and finally you measure it, and you'll get the outcome that you want. So from this circuits, again, just like in classical circuit design, you write an assembly code, for example, or a VHDL code, and then you build higher functions from it. You build the algorithms. There are many different algorithms in the quantum world, just like you have this linear search or Boolean bubble sort and quick sort. Similarly, in the quantum world, there are many different algorithms for different applications. I'm just listing some of them over here for communications, for simulating molecules, for optimization, which is a big thing in the core of machine learning. But there are more specialized machine learning algorithms as well, which, for example, QNNs are quantum neural networks. There are quantum versions of generative adversarial networks, VAEs as well. Yeah, so there's then cryptography, which is a very famous application, one of the earliest algorithms that showed that quantum computing can have a real world application. And there's also quantum search, which is also very general. And all these algorithms can be applied, again, for many different scientific fields. You see a lot of different scientific fields over here: chemistry, physics, math, computing, machine learning, biology. Some of the earliest ones which are very promising are, for example, encryption. So you want to encrypt your data, for example, in bank transactions. Then you have printerial simulations. That's, again, you can try to figure out properties. It might be drug design. It might be for many body physics. Optimization is, again, a very general applications of quantum computing. And finally, this is something that I personally worked on during my PhD. It's on personalized medicine, where you try to figure out what kind of DNAs and what kind of genomics can be used for designing or finding properties of different characteristics of life. So this is kind of my short presentation, and now I'll hand over to Achintya for the next part.